Section 9.4 is about sequences, and the harmonic sequence, where the denominators go up by 1, has a nice explicit formula, but the recursive formula is pretty difficult, so we don't talk about that. The Fibonacci sequence, on the other hand, has a pretty nice second order recursive formula. The explicit formula that does exist, but it's much more difficult, so we won't talk about that. The factorial sequence, 1 factorial, 2 factorial, 3 factorial, has both a explicit and a recursive formula that we could use. The triangular numbers, here they are, has a explicit as well as recursive formula. The triangular numbers are, if we look at these pictures of dots, the very smallest triangle, theoretically, has 1 dot, then a triangle with 3 dots, a triangle with 6 dots, a triangle with 10 dots, and every time we add a new row at the bottom of the triangle, pick up more dots, and that's the next number. Notice that there is a domain in each case of what values I can use for n. The way that I make sure that I've used the right domain is I make sure that the n value will never be smaller than 1. So for this case here, it has to be greater than 1. So when I plug in here, I'll have a sub 2, and here I'll have a sub 1, and then here I'll have a sub 3. So the third term will equal the second term plus the first term. So again, this is 1. Same here and here. Just make sure that when I plug in, so n has to be 2, but when I plug it in here, I get a sub 1, and that's the smallest I can possibly get. So just check to make sure that you can't get a sub 0. That wouldn't be good. The two main type of sequences that are in section 9.4 are arithmetic and geometric. Arithmetic we talked a lot about. That's where you start with a starting number, and you add a common difference. And then you add another common difference and another common difference. And that common difference can be plus or minus. And notice that the first common difference is added to get the second term. The second common difference is added to get the third term, which means to get the nth term, you would add n minus 1 common differences from your starting number. The way the textbook would write it is they would just switch the order of these two things. They write it this way. And that's the explicit formula. For the recursive formula, the first term is equal to whatever our first term is equal to. That's going to be a number. And then to get to the next term, we add the common difference, plus or minus, to our previous term. This is really linear, and our common difference is really the same as the slope in a linear equation. For geometric, it's really an exponential situation because instead of adding a common difference, we multiply by a common ratio. And a common ratio could be a positive or negative number that we multiply our initial value by. And so notice again, to get the second term, we multiply by the common ratio to the first power. To get to the third term, we multiply by the common ratio to the second power. So to get to the nth term, we multiply the initial value times the common ratio to the n minus 1 power. So there's our explicit formula. Our recursive formula is very similar to the recursive for the arithmetic, but instead of adding a common difference to the previous term, we multiply by a common ratio the previous term to get to the next term. So that's an exponential progression because we're multiplying each time. I've set up these equations so that for every case, n is greater than or equal to 1. I want to make a quick mention of alternating sequences. Those would be sequences that have a plus, then the next term is minus, the next term is plus, the next term is minus, alternates back and forth. For arithmetic, we can put a little negative 1 to a power in front of our explicit formula, and that would make it alternate. Or this one right here. It depends on whether we want the first term to be negative, because negative 1 to the first power is negative, or whether we want our first term to be positive. And so that would be negative 1 to the 1 plus 1 power, negative 1 squared, and that would be positive, and we'll start there. You might think you'd do the same thing for geometric and put a negative 1 to the n in front, But that's really not necessary because you just have to have the R value be less than 0, and it will automatically alternate because of the power here being an odd and an even number. Another thing we mentioned was the fact that sequences can converge, which means they ultimately arrive at a particular number, or like a horizontal asymptote, there's a certain Y value or answer that they get closer and closer to, or they diverge because they don't approach a particular number. Either they go to infinity or negative infinity, or there's a possibility that they will oscillate between more than two different numbers and never settle in. So one way of asking the question is we can ask for the limit as n approaches infinity, and that just means what is your limiting value? As n gets bigger and bigger, do you actually approach a particular thing, particular number rather, or not? Or we could just say, here you go, here's a sequence. Does it converge or diverge? And maybe not have this limit part. And so it would really the same question, but we'd have to use the words. Here we wouldn't need the words. Here we would need the words. Does it converge or diverge? Yeah, let's look at the answers to this. So here, if you have an arithmetic format, this is an explicit setup for arithmetic, it will definitely diverge because all lines, except for if they are horizontal lines, reach positive infinity when you go forward and make bigger and bigger n values or x values for linear. This is geometric, but it certainly looks like an exponential kind of an equation too if that had been x. So I'm thinking, okay, exponential, that's exponential growth. Oh, that equation just goes up really fast forever. So pretty sure that it'll be the same thing for a sequence, and it will be. So that would diverge. But in this case here, my R value is less than 1, so I'm multiplying by a fraction to get to the next term, and then multiplying by a fraction again. So that's exponential decay as it reduces, just as if that had been an x value. And just like the exponential equation with x and y, it will have a horizontal asymptote of y equals 0, so this will converge to 0 in the same way. Here we have an alternating, well, more than an alternating, it's an oscillating sequence, because it has some zeros in there as well. If the zeros weren't there, it would be alternating. But it never settles in. It's going to just keep bouncing back and forth here, so that's a divergent for the reason of oscillating. Here's an interesting strategy. Here I cannot plug in numbers. Well, maybe if I had a calculator, I could be plugging in here and evaluating. But if I look at the graph of the numerator, n, or that's sort of like x, like n, x. So y equals x, there's that graph, and ln n is kind of like ln x, so I look at that graph, and I can see that the numerator graph is always going to have a higher answer, or a higher y value, than the denominator graph. So it's going to grow much faster, and your fraction will get way top-heavy and head towards infinity, so that's divergent. If this had been flipped around, upside down, then it would have converged to 0. And maybe you can see that a lot of these converge to 0, but not all the time. Sure, we could come up with some for a pod or a quiz that converge to a different number. In this case here, the graphing thing is not really going to work, so I'm going to instead just plug in n values, like n is 1, n is 2, n is 3, and don't just look at the first couple, but do enough so you're like, whoa, the denominator is getting really big, way faster than the numerator, so yeah, it's going to converge to 0. All right, let's do some example problems from section 9.4. Here I've been given the 15th term's value, the 20th term's value, and I want to find the 6th term's value if it's arithmetic. Here I'm given enough values, or enough terms rather, the first 4 terms, so that I can determine that in fact it is arithmetic because it's going up by the same difference each time. Find the 200th term. Which term number would I have to go to get me an answer over 3,000? All right, looking at the answers, I have written these like 2 points, like an xy point, n, a sub n. And that allows me to find my slope, or my common difference, change in y over change in x. And then I'm going to write a point slope equation. But instead of using x and y, I'll use n and a sub n. And then I will just plug in my 6, that's like my x value, into the n's here and here, so that's a of 6, a sub 6, and get my answer. So I used a point slope strategy over here with my 2 points. Here I know the first term, so I'm going to do that arithmetic formula, which is really just the same as point slope, where I use the first term plus the common difference times n minus 1. And I have simplified this out because it makes it easier to plug into 200. 3 times 200 minus 6. Oops, yeah, 294. I'll fix that. And so then the first term that's greater than 3,000, I set 3,000 equal to my equation and solve it out to get n, but it did say greater than 3,000, so I can't use this. That's what it equals 3,000. So I'd have to do the next term up. If I were to have gotten a decimal answer, say the next time I do such a problem, just know that you can never have a decimal answer for a term number, so you still have to go up to the next n value or the next whole number. So there's an adjustment for this kind of question. A couple more problems here. We have, again, 2 terms, but this time it's geometric sequence, and we want the first term greater than 1,000,000. And we want the 20th term of this sequence here. Again, there's just enough terms to see that it is in fact geometric, not arithmetic, and we want the recursive equation. All right, in this first problem, I see that my initial value, even though it's the 5th term, my initial value is an 1/8. So remembering how to write an exponential equation, I'll put my initial value here, and I'll rig the exponent so that when I plug in 5, I'll get the 0 power. So 1/8 r to the 0 power, that just equals 1/8. So a5 equals 1/8. Then at this point, I can go a couple different ways. So one way I can do it is I can put in my 10th value and put in 10 for my n, 10 minus 5. And then I can solve out for r by multiplying both sides by 8 and taking the 5th root. There's one way you can do it. Now I have my r value. Now what I need to do is put 1,000,000 in for my explicit equation, set it up to my my equation that I've gotten, and multiply both sides by 8. I took the natural log of both sides. There's a couple different ways I could do it so that I get some trip and fall over here, and I can solve for n, which I then need to round up to the next whole number. Again, there are different ways that we have learned during the course of the year that you may have used to arrive at that same n value, so that's absolutely fine. To find the 20th term of this sequence here, I need to get my r value. So this first term times what gets me the second term? 5,000r is 4,000. Solve for r. Okay, there's my common ratio that I'm going to put right in here. There's my initial term, which I'm going to go under the assumption that that's the first term because they didn't say otherwise. So that's why it's just n minus 1, not n minus 5. And I'm good to go. I got my initial term and my common ratio. Now all I got to do is plug in 20 for n, and a of 20 equals my answer. The value of the term can be a decimal. That's not a problem. The term number cannot be a decimal. To write this recursive equation, my first term is 5,000, and to get the next term, I multiply the current term by 0.8, and then be careful what n can be here, greater than or equal to 1, so that I don't get n equaling a sub 0. I don't need that in my equation.